This presentation is about COVID-19 detection and treatment using artificial intelligence. The reason for researching this topic is because current COVID-19 tests are not very accurate. Currently, RT-PCR tests are given to people who may have symptoms of COVID-19. However, this test has a false positivity rate between 2 and 29%, giving false positives about one-third of the time, leading to only a 71 to 98% sensitivity. Artificial intelligence is a machine-based learning technology that has the capability to detect coronavirus with a higher sensitivity percent and range, and there are many methods in which this can be done. One way is through using neural networks. Neural networks, or deep learning, is when the computer performs tasks through training. A neural network consists of layered nodes that are connected to upper and lower layers. These connections are given a weight that determines if the connection will fire or pass data to the upper layer, depending on a threshold value. Neural networks that have large computational power and training sets are quick and accurate, perfect for medical applications. COVNET is a convoluted neural network that uses CT scans of the chest to diagnose COVID-19. This kind of neural network takes in an input image and assigns a weight to objects in the image to help distinguish between them. Through this, COVNET is able to differentiate between CAP, or community-acquired pneumonia, and COVID-19. The COVNET framework also consists of ResNet50 as the backbone of the architecture, which is what detects COVID-19.
In order for COVNET to detect COVID-19, COVNET takes in a series of chest CT scan slices processed with UNet-based segmentation as input. You can see an example of this on the right. The AI will then mark features of interest on each scan. These features are then combined into a map using max pooling, which calculates the largest value of each feature on the feature map. The complete feature map is then used to generate a probability score for COVID-19. As you can see from the following table, COVNET's performance is quite good. For COVID-19, it has a sensitivity of 83% to 94% and a specificity of 93% to 98%. COVNET's performance is much better than RT-PCR's performance. COVNET's sensitivity is 83% to 94%, where RT-PCR's performance is 71% to 98%. COVNET, while fully trained, takes only 4.51 seconds to find a result, while RT-PCR takes several days. Knowledge graphs are a human and machine-readable graph of entities that are connected by edges. On the right, the edges are represented by green and red arrows. Entities are represented by blue circles. Knowledge graphs are used in AI with machine learning to reduce the use of large label datasets, facilitate transfer learning and explainability, and encode knowledge too costly to learn from data alone. For medical purposes, knowledge graphs are helpful for finding a drug that interacts in a specific way to a virus or a gene.
Now that we have a better understanding of what knowledge graphs are, let's take a look at a specific example of how knowledge graphs were used to find potential vaccines for COVID-19. The Benevolent AI Trials was a study that created a comprehensive COVID-19 knowledge graph called COVID-KGE. COVID-KGE is a knowledge graph-based deep learning methodology that aims to repurpose existing drugs for COVID-19 treatment. The knowledge graph used 24 million research articles and consisted of 39 types of relations and over 15 million edges. The relationships were among drugs, treatments, and diseases. Using the Amazon Web Services computing resources and graphical representation learning techniques, Benevolent identified 41 repurposed drug candidates for COVID-19 treatment. DGLKE is the knowledge graph learning package used in COVID-KGE. This package accelerates training on knowledge graphs with a set of models that include Rotate-E to learn of relationships between entities and relationships. In the Rotate-E model, relationships between two objects are defined as a rotation from the head entity to the tail entity in the complex vector space. When there is a match between entities, it minimizes the distance between the head and tail entities. Otherwise, it maximizes this distance. More specifically, if we take a look at the equation on the top right of the screen, and we let H and T be the vectors corresponding to the head and tail entities, respectively. Then R is the vector corresponding to the relationship type, and rotate E tries to minimize this distance when the relationship of R is positive. After mapping the existing drugs, the coronavirus sample, and the treatment relationships between the drugs and the virus to the complex vector space using rotate E, the top 100 most relevant drugs were selected as candidates for repurposing to treat COVID-19. If we take a look at the diagram in the bottom right, we can see that there are different treatment options. Distance to the coronavirus represents the priority of that drug option. For example, the red pill on the top represents a drug treatment which has a low priority because its distance from the coronavirus object is much higher than the ones of the yellow pills.